Men and metals have an age-old relationship. Different periods of early human civilization have been named after metals. The attributes of gold influenced the mind and heart of Indians so much that they conferred upon the Supreme Spirit the designation of Hiranyagarbha. It was so called because he remains in a golden egg as an embryo. The Rig Veda has widely referred to Hiranya, which is the oldest Sanskrit word for gold. The Mahabharata referred to Piplika gold, that is Ant's gold. Heaps of this type of gold was presented to the king Yudhishthir at the time of Rajasuya Yajnas. Piplika gold was powdery in nature and of high purity. Kautilya described a variety of gold called Rasvidha, which was naturally occurring dissolved gold in liquid form. He stated that one pal was a measuring unit, of this solution converts 100 palas of silver or copper into gold, which refers to the cementation of gold on the surface of metals like silver and copper. Kalidas also mentioned such gold solutions and termed it Kanakras. According to Will Durant, Hindus seem to have been the first people to mine gold. Greek visitors like Megasthenes have mentioned this in their records. Much of the gold used in the Persian Empire in the 5th century BC came from India. Some of the gold and silver ornaments from Indus Valley sites, such as Mohenjo-daro, are hosted in the National Museum, New Delhi. The deepest ancient mine in the entire world is found in the Musky region of Karnataka. After elaborate carbon dating, it was found that the mines can be dated back to the 1st millennium BC. It is known that there are some 44 old texts that describe the process of Indian metallurgy. One of the most well-known of these texts is called the Ras Ratna Samuchaya. In it, we find descriptions of many aspects of this technology, including the structural arrangement and function of the chemical laboratory. The Koshti Yantra, the furnace, the Tiryak Patan Yantra, vessels for containing chemicals, the Dekhi Yantram, the distillation pot, and other things like the chemical work to be done in the laboratory. An influential Indian metallurgist and alchemist was Nagarjuna, who was born in 931 contemporary era. He wrote the treatise Ras Ratnakar that deals with preparations of compounds. It gives a survey of the status of metallurgy and alchemy in the land. Extraction of metals such as silver, gold, tin and copper from their ores and their purification were also mentioned in the treatise. Silver ornaments that had been found at Kunal, Nadar Saraswati site, proved that copper purification, which releases silver as a byproduct, was known in India before 3000 BC. In this context, it is interesting to note that the law governing the solubility of gases in metals, known as Sieberd's law, came into existence only in the early 20th century. However, ancient Indians recognized the practical aspect of Sieberd's law in judging the purity of silver. Kautilya also described the method of refining silver. There is a rich Sanskrit terminology for metals from which interesting information on history of metals can be derived. Silver has a tendency to tarnish. It tarnishes readily when exposed to atmosphere containing sulfur and looks blackish. Due to this characteristic, an uncommon Sanskrit name of silver is Durvarna. Tin recovered from lead tin alloy was called Nagaj, that is, that obtained from Naga, means lead. Similarly, tin recovered from the impure gold containing tin was called Swarnaj. Zinc is one of the most difficult metals to smelt, but ancient Indian metallurgists had mastered the technique of smelting zinc, as is evident from the semi-industrial scale production of zinc in the Zevar region of Rajasthan. Owing to the high volatility of the metal while smelting of the same, a unique technique of downward distillation was developed by the ancient Indian smelters. Nagarjuna's Ras Ratnakar elaborately describes the method of zinc smelting. The elegant Bidri ware of the Bidar province of Hyderabad was another remarkable example of artistic innovation. The impressive articles with a unique inlaid alloy of zinc were extremely popular in those days. Indians were the first in the then known world to have successfully developed the extraction of zinc from its ores. They had understood the complicated nuances of zinc metallurgy, its endothermic reduction reaction, and the reducing atmosphere needed for the downward distillation of zinc even as early as 400 BC. It was only 2000 years later that a similar process was adopted in the West. Brass, an alloy of copper and zinc, was known to men much earlier than they were able to extract zinc from its ore on a large scale. Zinc oxide, known as Pushpanjan, has been referred to in Charak Samhita. Ras Ratnakar provides the earliest documentary evidence for the cementation process for brass making and reduction distillation process for zinc extraction. Ancient northwestern India is the earliest known civilization that produced zinc on an industrial scale. References in Greek text to zinc technology indicates that zinc objects were traded from India as far as 6th or 5th century BC. From India, this technology reached China. China exported zinc to Europe under the name of Totemu or Tutanag. The term Tutanag may derive from the South Indian term Tutanaga, which is a term given to zinc there. In 1738, William Champion is credited with patenting in Britain a process to extract zinc from calamine in a smelter. His first patent was rejected by the Patent Court on grounds of plagiarizing the technology common in India. However, he was granted the patent on his second submission of patent approval. The Rasratna Samuchaya of 800 contemporary era explains the existence of two types of ores in zinc metal, one of which is ideal for metal extraction while the other is used for medicinal purpose. It also describes two methods of zinc distillation. Europe learned to produce zinc in 1746, but it was distilled in India more than 2000 years earlier through the use of a highly sophisticated pyrotechnology. If we talk about steel, Indian crucible steel was a celebrated material worldwide. It was usually produced by simultaneous carburization and melting of wrought iron in closed crucibles. Kautilya termed it vrat because it was of circular shape. Some of the accounts of the Greek travelers mention the Indian process of steel manufacture as the crucible process. The Greek account mentions the word voutes, which originates from ukku, a term that was widely used across Karnataka and Andhra Pradesh to denote steel. Arab Idrisi says, the Hindus excel in the manufacture of iron. It is impossible to find anything to surpass the edge from Indian steel. Both steel was widely exported and traded throughout ancient Europe, China, the Arab world, and became particularly famous in the Middle East, where it became known as Damascus steel. Mercury was also very popular in ancient India owing to its alchemical significance. Kautilya's Arthashastra is the earliest reference of the distillation process that was used for the extraction of mercury. Vermilion or cinnabar, which has extreme ritualistic significance in the Indian tradition, is made from mercuric sulfide. It was also used for making the red bindi, which is widely worn on the forehead by the Indian women. Copper was another metal that the people of ancient India learned how to use expertly. From as far back as 2000 BCE, people had made fine copper axes with sharp cutting edges by casting the copper in molds. In Harappa, evidence of some copper smelting furnaces have also been found. The Ras Ratna Samuchaya describes the extraction and use of copper. Copper and its alloys were also used to create copper bronze images, lamps, and razors for the tonsure ceremony. One of the most important sources of history in the Indian subcontinent are the royal records of grants engraved on copper plate grants known as Tamrapatra. Because copper does not rust or decay, they can survive indefinitely. The world-renowned bronze sculpture statue of the dancing girl from Mohenjo-daro is the best example of the tin mining and smelting technology in ancient India. The Arthashastra lays down the role of the director of metals, the director of forest produce, and the director of mining. It is the duty of the director of metals to establish factories for different metals. The director of mines is responsible for the inspection of mines. The trade of metal products was extensive between India, Egypt, and Rome. An important metal referred to in Rigveda is Ayas. It has a shining appearance. Ayas has different meanings in different periods. In early Vedic period, it means either copper or copper alloys. One of the important products made from Ayas, as stated in the Rigveda, was the weapon of Indra called Vajra. In the later Vedic period, Ayas or Krishna Ayas means iron. The iron pillar, known as the Mehrauli pillar inscription, weighing over 6 tons, more than 7 meters tall, is constructed in the single forge and is erected on the top of Vishnupad hill, which is in modern central India. It has Sanskrit inscriptions on it in the Brahmini script about the great Gupta ruler Chandragupta Vikramaditya during the Gupta dynasty's rule in 320 to 540 AD. Later, the Tomar king Angpal brings it to Delhi and installs it in its current place. What's so wonderful about it? Well, one should ask, what's so mysterious about it? More than 1600 years back, to build an iron pillar of this huge size in a single forge itself is an indication of an advanced metallurgy of the ancient Indians. Even in today's modern technological world, it is a great achievement to forge such a huge pillar in a single forge. But there's more. This pillar, which contains more than 98% of pure iron, even after 1600 years, has not got rust. It is 100% corrosion resistant in spite of the fact that it is 98% iron. This indicates one of the great technological achievements of the ancient Indians. Corrosion resistant technologists from all over the world have studied this pillar. Even the pollution of Delhi has not touched it. It is still not rusting. And the other one is near Bangalore in Kannur, where there is 750 centimeters of rain a year, 6 to 8 months, and this has been there for 2400 years and it is rust proof. About the second pillar, what is more interesting is that it was built not by any expert, it was built by the tribal, the aboriginals of that area to welcome Adi Shankaracharya when he came to their village. So this technology was there not only with the learned ones, it was available to the tribals even. The spread out of these pillars across the geographical landscape of India indicates that the iron pillar of Delhi was not a single isolated incident of the ancient genius, but was a common technical knowledge of the ancient civilizations in the country. Indians were far ahead of Europe experts in several technologies involving melting, smelting, casting, calcination, sublimation, steaming, fixation, and fermentation. They were experts in the preparation of a variety of metallic salts, compounds and alloys, pharmaceutical preparations, distillation of scents for making perfumes and fragrances as well as cosmetics. Nearly 3000 years back, Indians knew the art of making glass and coloring it with metal salts. In ancient India, glass was used to make beads, bangles and laboratory ware. It is appropriate to mention that it is the Muslims who took much of the Hindu chemistry, medicine, astronomy and mathematics and other branches of science and technology to the Near East and then to Europe. It is well established that the secret of the manufacturing of Damascus steel was taken by the Arabs from Persians and the Persians from India. If you want to know more about science in ancient India or scientists in ancient India, please check the playlist Science in Ancient India or Ancient Indian Scientists. It will not be an exaggeration of the facts if we say that mathematics was at its heights of glory in ancient India. The earliest available text, Rig Veda, is a living example of the fact that the entire Samhita is written on various meters known as chandas. Like you can see, Gayatri Chand or Gayatri meter has 3 lines and 8 syllables in each line. In Ushnik, we have 3 lines and then 8 and 8 syllables in first 2 lines and 12 syllables in the third line. And same way, you can see the details of Anushtub, Bhrati, Pankti, Trishtub and Jagati. The entire 1028 verses of Rig Veda are written on 1 meter or the other, which clearly indicates that mathematics was so deeply entwined in ancient Indian lifestyle that the entire communication was done mathematically. The very famous Gayatri Mantra is known as Gayatri Mantra not because it is devoted to goddess Gayatri, but because it is written on Gayatri Chand, as we find not only one but various Gayatri Mantras in the Rig Veda devoted to various deities like Hanuman, Lakshmi and many others. The Gayatri Mantra has 3 lines and 8 syllables in each line, as you can see in this picture, which brings it to a total of 24 syllables. We find mention of powers of 10 from 100 to trillion. The words mentioned in Vedic period, Laksh, that is lakh, and Koti, that is crore, are still in use today. Yajurveda is all about the knowledge of yajnas, and we see that the Shulba Sutras were made to design yajna altars mathematically. They could circle the square and square the circle. Opening lines of Shukla Yajurveda itself tells about the concept of infinity. Infinity is born out of infinity, and when we take infinity out of infinity, only infinity is left. Anything divided by infinity is zero. The word used for infinity was Anant, which literally means endless. Samved, which is said to have given birth to the entire music on the globe, is actually Rig Veda set to music, where the verses already set to chandas or meters are further set to various ragas by adding mathematical notations to the word. Out of 6 compulsory subjects which were prerequisites for those who wanted to know the Vedas, Chand or meter and Jyotish or astronomy were designed to give vivid knowledge of mathematical concepts and mathematical cosmology. The Bodhayan Shulbasutra contains several early mathematical results. He has done research on circle, square, rectangle and triangle. Discovered pi to some degree of precision. When constructing circular shapes, Bodhayan uses different approximations of pi. Bodhayan even tried to find a circle whose area is the same as that of a square. Draw half its diagonal about the center towards the east-west line, then describe a circle together with a third part of that which lies outside the square. Bodhayan discovered Pythagoras' theorem much before Pythagoras was born. A shloka from the Shulba Sutra is proof that he had the concept of Pythagoras' theorem in his mind even before Pythagoras was born. Tirgha chatushrasya kshanya rajuhu parshvamani tiryagmani chayat prathag bhute kurutas tubhyam karoti. It means a rope stretched along the length of the diagonal produces an area which the vertical and horizontal sides make together. He judged the square root of 2 to 5 decimal places of accuracy. The Sanskrit text gives in words what we would write in symbols like, which is to 9 places and is correct to 5 decimal places. The air is of the order of 0.002 only. Aryabhatta calculated the circumference of the earth. According to him, the circumference of the earth is 39,968.05 kilometers, which is just 0.2% less than today's calculation of 40,075.01 kilometers. Aryabhatta offers a huge amount of information on algebra, arithmetic, quadratic equations, and trigonometry. He was essentially responsible for the birth of trigonometry, which the whole world is studying today. In fact, sine, cosine are transcriptions introduced by Aryabhatta. Aryabhatta called them ja and koja. Aryabhatta had devised an inventive way of writing numbers as symbols so that they could be integrated into the form of the verse. Many times you might have heard that Aryabhatta invented zero, but actually he started using zero as a symbol. It was Maharishi Pingal, a Sanskrit scholar, who used binary numbers in the form of symbols in 300 BC. Western scholar Gottfried Leibniz came up with this concept just 300 years ago in the 17th century. In the works of Pingal, zero is known as shunya, which means nothing. This concept of nothingness has been integral part of Indian culture, as is mentioned in Rig Veda also. From nothing came everything. Aryabhatta, in his Aryabhatya, has used zero a plenty of times and has given name to each place value, which became the base of the modern decimal system. This great Indian mathematician calculated the value of pi at 3.1416. Varahamihir improved the accuracy of the sign tables of Aryabhatta. He defined the algebraic properties of zero as well as of negative numbers. Furthermore, Varahamihir was among the first mathematicians to discover a version of what is now known as the Pascal's triangle. He used it to calculate the binomial coefficients. He created the first 4x4 magic square. Varahamihir was the first to specify that the Ainamsh or the shift of the equinox is 50.32 seconds. This value is very important for the modern day geostationary satellites. Bhaskar too, in his book Siddhanta Shiromani, written in 12th century AD, has told about calculus. Calculus means mathematical study of continuous change. He mentioned all the primary concepts of calculus: infinite simul calculus, differential calculus, and integral calculus. Although the modern world recognized Gottfried Leibniz of 17th century as the father of calculus, whereas it was discovered by Bhaskar too 500 years before him. The oldest extant mathematical manuscript in South Asia is the Bhakshali manuscript, a birch bark manuscript written in Buddhist hybrid Sanskrit in the Sharada script, which was used in the northwestern region of the Indian subcontinent between the 8th and 12th centuries contemporary era. The manuscript was discovered in 1881 by a farmer while digging in a stone enclosure in the village of Bhakshali near Peshawar, then in British India and now in Pakistan, of unknown authorship and now preserved in the Bodleian Library in Oxford University. The surviving manuscript has 70 leaves, some of which are in fragments. Its mathematical content consists of rules and examples written in verse, together with prose commentaries, which include solutions to the examples. The topics treated include arithmetic, that is fractions, square roots, profit and loss, simple interest, the rule of three, and regular falsi, and algebra, that includes simultaneous linear equations and quadratic equations, and arithmetic progressions. In addition, there is a handful of geometric problems, including problems about volumes of irregular solids. The Bhakshali manuscript also employs a decimal place value system with a dot for zero. Ancient Indians not only had advanced knowledge of mathematics, but they had mastered the art of encoding also. If you want to know more about ancient Indian mathematicians, please watch the playlist Ancient Indian Scientists.
India was a world guru and has made world's largest contributions in the field of science and technology. Civil engineering in ancient India was known as Sthapatyakala, and term Vastu originally derived from the root word vas, meaning to dwell or a dwelling place. Art of architecture and construction in ancient Indian texts is called Vastu Vidya. Marvelous monuments in India are examples of Vastu Vidya, which represent its advanced architectural and constructional techniques. Methodology of construction of these monuments represents harmony of structure with environment, rituals, and lifestyle of people of India. The details of Vastu had been rigorously dealt across various ancient treatises like Vishwakarma's Vastu Shastra, Rishi Phrigu's Phrigu Samhita, Maya Mattam, said to be written by sage Maya Muni, Samrang Sutradhara of Bhojdev, and Aparajita Prach. These technical treatises contain elaborate descriptions on the aspects of architecture and engineering. Entire universe, including our body, is composed of five basic elements: air, earth, fire, space, and water, called Panch Mahabhut. The main principle of Vastu is to maintain the balance between dwelling structure and the elements of universe for happiness and comfort. Vastu is the science of direction that combines all the five elements of nature and balances them with the man and the material. This is how the arrangement of Panch Mahabhut with respect to cardinal directions has been done on a map. There are five basic principles on which the great edifice of the Vastu science of architecture stands. First is Bhu Pariksha, which means examination and selection of site. It is a unique method of testing the site before it is selected for the construction. The soil has to be examined for its shape, contour, odor, color, taste, and touch. Second is Tik Nirnay, that is orientation. According to Indian texts of architecture, the cardinal directions hold a particular significance. The various associations are given to the eight cardinal directions. Main aim in orientation principles of Vastu Shastra is setting of structure and its components in such a way that they may get maximum benefits from solar energy and wind. These directions are north, northeast, which is known as Ishan, east, southeast known as Agni, south, southwest known as Nairitya, west and northwest known as Vayavya. Third is Vastu Purush Mandal known as Padvinyas, which means planning of various components. It constitutes mathematical and diagrammatic basis for generating design. Purush refers to energy, power, soul, or cosmic man. Mandal is the generic name for any plan or chart which symbolically represents the cosmos. Padvinyas is the process in which the site is divided into various numbers of squares. The number of squares varies from single square 1 into 1 grid to 32 into 32 1084 squares depending upon type of construction, where each square is referred to be as pad. Most common mandal is where deities are assigned to the divided squares and are named after the deity assigned. It defines stable structural grid for construction. This is the diagram of Vastu Purush Mandal and is divided into 9 into 9 equals 81 parts. The position of the 45 gods who are holding down the Vastu Purush are shown. 32 are in the external enclosures and 13 are in the internal enclosures. These symbolic gods rule various aspects of life and have certain inherent qualities. Fourth is proportion and measurement of building, known as Man and Ayadi. Man prescribes the proportionate measurements. The measurements are divided into categories such as measurement of height, breadth, width of circumference, measurement along plumb lines, measurement of thickness, and measurement of internal space. Ayadi principles are useful for calculating proportion and scale of different components, principles of ratio of breadth and length, height and length, etc. And the fifth is Bhulambman or Chand, which is the aesthetics of the building. These principles are based on movement of celestial elements like planets, sun, moon and their effects on environment, velocity and direction of wind, rainfall, volume and intensity and characteristic of soil. These principles are also derived on the basis of special characteristics and influences of elements of universe such as the magnetic field, gravitational effect of earth and galaxies in sky, light and heat of the sun, etc. It reflects Indian philosophy of life and interrelationship between human and environment. Before I take you to a journey of ancient Indian architecture, let me tell you that even prior to marvelous ancient Indian architecture marvels of architectural knowledge of Indians can be witnessed even in the prehistoric sites of Indus Valley civilization. Let us now have a journey of civil engineering and architecture of prehistoric times, that is Indus Valley civilization. India's urban civilization, traceable to Mohenjo-daro and Harappa, were planned urban townships existed 5000 years ago. From then onwards, the ancient Indian architecture and civil engineering continued to develop and grow. The people of Indus Valley civilization were great builders. The excavations carried out at different sites connected with Indus Valley civilization show that the people of the Indus Valley led a highly advanced urban life. Both Mohenjo-daro and Harappa were models of careful town planning. The principal streets all ran in straight lines either from north to south or from east to west in grid pattern, and in places the main roads were 30 feet wide so that cars could pass without difficulty. The fronts of the houses were carefully lined up and no one was allowed to have the frontage of his house projecting beyond the building lines. There were no narrow side streets. Houses at street corners were slightly rounded to make the flow of traffic easy. Each street had a small watercourse covered with stone for drainage purposes. The twin cities of Mohenjo-daro and Harappa grew accordingly to a central plan that had been conceived at their foundation. The cities, dominated by fortified citadels, were carefully planned with their own water and sanitation systems and streets of brick-built houses laid out in a grid pattern. The elaborate drainage system was a unique feature of the city. Almost every house had a well, drains and comfortable bathrooms, for which pottery drain pipes and receptacles were laid down, communicating them with the street drain of gutter. The main drains were provided with manholes at regular intervals for regular inspection and clearance. The cities were fairly large and skillfully designed. The dwelling houses were many and they varied in size from a big building with 2 rooms to a palatial structure having a frontage of 85 feet and a depth of 97 feet. The outer walls were 4 to 5 feet thick. The houses were built strongly of well-burnt modern-looking red bricks cemented together with dried mud. The houses were very plain with narrow doors, flat roofs, no ornamentation and no windows. Inside, they offered a high degree of comfort. Many of them had spacious bedrooms, living rooms and guest rooms, a bath, running water, a fresh water tank and an enclosed garden. The big houses had 2 or more stories. They were finished with paved floors, courtyards, kitchens with raised platforms, excellent doors, windows and narrow stairways. In addition to dwelling houses, there were a few spacious buildings of elaborate structure and design. Some had large pillared halls. They were supposed to have been palaces, temples or municipal or public assembly halls. Among the larger buildings, the Great Granary is the most remarkable and the largest building discovered at Harappa. It measures 6.15 meters by 15.5 meters. The granary was built with sufficient knowledge of natural ventilation to prevent the grain from becoming mildewed. The most important structure in the city was the Great Bath. It consisted of a large quadrangle in the center with galleries and rooms on all sides, in some of which there were arrangements for hot water bath. The water was discharged by a large drain with a corbelled roof more than 2 meters in height. The Great Bath is 60 meter long and 36 meter wide, and its outer walls are about 2.6 meter thick. In the center of the quadrangle was a large swimming enclosure 13 meter long, 7.5 meter wide, and about 2.5 meter deep. It had a flight of steps at either end and was fed by a well situated in one of the adjoining rooms. We have even found a dockyard in Indus Valley civilization in Lothal, situated near modern Ahmedabad. Lothal engineers accorded high priority to the creation of a dockyard and a warehouse to serve the purposes of naval trade. The dock was built on the eastern flank of the town and is regarded by archaeologists as an engineering feat of the highest order. It was located away from the main current of the river to avoid silting, but provided access to ships in high tide as well. It is speculated that Lothal engineers studied tidal movements and their effects on brick built structures. Since the walls are of kiln built bricks, this knowledge also enabled them to select Lothal's location in the first place, as the Gulf of Khambat has the highest tidal amplitude and ships can be sluiced through flow tides in the river estuary. The engineers built a trapezoidal structure with north-south length of average 215 meters, that is 705 feet, and east-west width of 35 meters, that is 115 feet. The warehouse was built close to the Acropolis on a 3.5 meter high podium of mud bricks. The rulers could thus supervise the activity on the dock and warehouse simultaneously. There was an important public building opposite to the warehouse whose superstructure has completely disappeared. Throughout their time, the city had to brace itself through multiple floods and storms. Dock and city peripheral walls were maintained efficiently. The town's zealous rebuilding ensured the growth and prosperity of the trade. All the construction were made of fire-dried bricks, lime and sand mortar, and not by sun-dried bricks, as bricks are still intact after 4,000 years and still bonded together with each other with the mortar bone. The city was divided into a citadel or acropolis and a lower town. The rulers of the town lived in the Acropolis, which featured paved paths, underground and surface drains built of kiln-burned bricks and potable water well. The lower town was subdivided into two sectors, a north-south arterial street with the main commercial area. It was flanked by shops of rich and ordinary merchants and craftsmen. The residential area was located to either side of the marketplace. The scientific survey of Indus Valley civilization clearly provides an engineering feat of the highest order. Please check the next video for the jaw-dropping marvels of civil engineering in ancient India. If you want to know more about science and technology in ancient India, please check the playlist Science and Technology in Ancient India, wherein you can find videos on mathematics, astronomy, alchemy, metallurgy, and other such subjects, and also scientists of ancient India, wherein you can find videos on astronomers, mathematicians, alchemists, surgeons, and other scientists of India.
Beginning of agriculture in India. Agriculture in India is not of recent origin, but has a long history dating back to Neolithic age. It was one of the main reasons of Neolithic revolution. It changed the lifestyle of early man from nomadic hunter and gatherer to cultivator of land. In the Neolithic period, roughly 8000 to 5000 BC, agriculture was far from the dominant mode of support for human societies, but those who adopted it flourished. The birth of agriculture was revolutionary as it brought the very first agricultural revolution, not just in India but all around the globe, and it also brought the settled lives to the early people and hunter-gatherers now started to settle to grow cereal crops like ragi, horse gram, rice, wheat and barley. With farming, domestication of cattle, sheep
and goat also started, as agriculture and domestication of animal go hand in hand. Polished stone axe and sickle were used for clearing and cleaning bushes and to prepare field for cultivation of crops. Archaeologists have found the first reference of pottery in this age, and it might have been used for storing food grains. Agricultural communities became widespread in Kashmir Valley around 5000 BC. It was reported that cotton was cultivated by 5000 to 4000 BC in Kashmir. As early as 4530 BC and 4440 BC, wild urziya rice appeared in the Balan and Ganges Valley regions of northern India. Earliest evidence of agriculture is found from Mehergarh, which is now in Pakistan, which dates back to 7000 BC. The excavation of Mehergarh period sites, that is around 8000 to 6000 BC, throws some startling facts about Indian agriculture that began as early as 9000 BC. The domestication of plants and animals are reported in the subcontinent by 9000 BC. Wheat, barley, and jujube were among common crops. Sheep and goats were among animals that were domesticated. This period also saw the first domestication of the elephants. With implements of techniques being developed for agriculture, settled life soon followed in India. Double monsoons that led to two harvests being reaped in 1 year in the country facilitated the settled mode of production. In the Indus Valley civilization, agriculture was generally practiced along the river banks, most of which were flooded during the summer and monsoons. This flood every year deposited fresh alluvial silt, which was highly productive and for which no major furrowing and certainly no manures and irrigation were required. Harappa, Mohenjo-daro, Dholavira, Rakhigadi and Ganeriwala, these were major sites of Indus Valley civilization. In Kalibangan, we have found an evidence of plough. A wooden plough with a copper or wooden plowshare was used for tilling fields. A cultivated field excavated at Kalibangan shows crisscross furrow marks indicating that crops were grown simultaneously. Mixed farming was the basis of the Indus Valley economy. This method is followed even today in Rajasthan, Haryana, and western Uttar Pradesh. The Indus Valley civilization was largely dependent on the Indus River system. As a result of the river's highly nutritious water, the Indus Valley was able to produce great surplus of food for their civilization. The Indus River patterns also created a flood season that farmers were able to take advantage for the irrigation purposes. The river contributed to crop health with fertilization and irrigation. Farmers took advantage of this by sowing seeds immediately after flooding to quickly begin growing a new crop of produce in the perfect soil. Harvesting of crops would have been done with copper sickles as well as stone blades hafted in wood. Irrigation was developed in the Indus Valley civilization by around 4500 BC. The size and prosperity of the Indus civilization grew as a result of this innovation. It eventually led to more planned settlements making use of drainage and sewers. So, as per the Neolithic age, we didn't use any kind of tool, but now in this stage we were plowing and we had knowledge about the soil's health, that we used crisscross pattern, and also we used copper sickles as well as stone blades for harvesting crops. The crops they have produced were wheat, barley, sesame, mustard, lentil and chickpea. These are some chief crops of Indus Valley civilization, but principal cereals were wheat and barley. Remains of rice have been found from Lothal in Gujarat and Rangpur in Haryana. Traces of millets have also been found from the sites in Gujarat. 6 varieties of millets including ragi, kodon, sanwa and jowar were cultivated along with peas and beans. Other major crops include dates, sesame and mustard. Indigo cultivation was evidenced at Rojdi in Gujarat. Cotton has been found at Mehergarh at least 2000 years before the mature phase of the civilization. This is the oldest evidence of cotton in the world. The Indus cotton industry was well developed and fragments of cotton cloth are found at Mohenjo-daro. The Indus Valley civilization was producing surplus, so there we discovered the granaries. Archaeological evidence of an animal-drawn plough dates back to 2500 BC. Some animals thought to be vital for survival were worshipped. Trees were also domesticated and worshipped. Varaha Meher wrote Vrihad Samhita, which was about agriculture, plant production from insects and manuring. Amarkosh, a book by Amar Simha, contains information on soil irrigation and agricultural implements described 12 types of lands. If you want to know more about science and technology in ancient India, please check the playlist Science and Technology in Ancient India, wherein you can find videos on history of astronomy, history of mathematics, history of metallurgy, and such other topics. Thank you.